Tonight, we're going to look at the only other world where rain falls from clouds, gathers into rivers, cuts canyons through solid ground, and pools into seas deep enough to lose a ship in, and where not one drop of it is water. The surface of that world sits at about minus 179 degrees Celsius. That single number reorganizes everything. At that temperature, water is not a liquid. It is not even a substance that moves. It is stone. The ground on Titan is water, frozen so hard that rivers cut valleys into it the way rivers on Earth cut valleys into limestone. The cliffs are ice. The gravel is ice. The seafloor is ice. And the liquid running over all of it, filling the channels and standing in the basins, is methane. The same molecule that arrives through a household gas line and burns blue on a kitchen stove. Stand on that shoreline, and every category you brought with you comes apart. The rock is not rock. The sea is not water. The rain that streaks the sky above you is fuel. And the air holding that rain together is being taken apart by sunlight faster than anything we can see is replacing it. That is the part nobody can explain yet. Titan runs a complete weather system on a fluid that should have run out tens of millions of years ago, and the seas we can measure are nowhere near large enough to have been the supply. So the question tonight is not whether the rivers are real. They are real, they are mapped, and one of them holds liquid today. The question is why the system is still running. By the end of tonight, you're going to understand exactly what Titan's liquid is made of, what we have actually observed of the rain as opposed to what we have modeled, and why the people who work on this moon will tell you plainly that they do not know where the methane comes from. Before we get started, if you love exploring the outer solar system as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Titan was found on the 25th of March, 1655, by the Dutch astronomer Christian Huygens, working with a telescope he had built himself and a lens he had ground by hand. It was the first moon anyone had discovered around Saturn, and for a long time it was simply a point of light that kept its distance from the rings. What Huygens could not have known is that he had found the largest reservoir of surface liquid outside Earth, and that it would take 3.5 centuries for anyone to see a single feature on it. That delay is the first fact worth holding on to. Titan is not small. Its radius is about 2,575 kilometers, which makes it nearly 50% wider than our own moon and the second largest moon in the solar system. It is larger across than the planet Mercury. Through a good telescope, it should have been a disk with markings, the way Mars is a disk with markings. Instead, for 350 years, it was a featureless orange ball. The reason is an atmosphere, and it is not a thin one. Titan is the only moon in the solar system with a substantial atmosphere, and by one important measure, it is denser than ours. The pressure at Titan's surface is roughly 60% greater than the pressure at sea level on Earth, comparable to the pressure you would feel about 15 meters underwater. That is a genuinely strange arrangement. A body with 1/7 of Earth's surface gravity is holding on to more atmosphere per square meter than Earth manages, because the atmosphere is so cold that its molecules move too slowly to escape. The composition is about 95% nitrogen. In that respect, Titan's air is the closest thing to our own that anyone has found. But the remaining few percent is where the world diverges. About 5% methane near the surface, plus a long list of heavier carbon compounds produced when sunlight breaks that methane apart high above. Those products are the reason no one could see the ground. Ultraviolet light, arriving weakly at Saturn's distance but arriving continuously, splits methane molecules in the upper atmosphere. The fragments recombine into ethane, acetylene, propane, and progressively larger chains, and the largest of them condense into a fine aerosol that never fully clears. The result is a photochemical smog wrapped around the entire moon, layered, orange, and optically thick. Sunlight gets through it, scattered and softened, but images do not. From Earth and from every flyby before the modern era, Titan simply refused to show its face. The smog is also the first clue in tonight's problem. Every one of those haze particles is made from methane that has been destroyed. The haze is not weather, it is exhaust. The surface was finally seen on the 14th of January 2005 by a probe named after the man who found the moon. Huygens was a European-built lander carried to Saturn aboard NASA's Cassini spacecraft, released on a ballistic path and left to fall. It entered Titan's upper atmosphere at speed, shed that speed against the thick air, deployed a sequence of parachutes, and then drifted downward for about 2 hours and 27 minutes. It was the most distant landing ever attempted, and it was a one-shot descent. There was no second probe, no retry, and no way to steer. For the first part of the fall, the cameras saw exactly what everyone expected: uniform orange in every direction without a horizon. Then, somewhere around 40 kilometers up, the haze began to thin, and a landscape resolved underneath it. It was drainage. That is the word the imaging team used, and it is the correct one. Branching networks ran down from bright elevated terrain into a darker, flatter plain. The networks had the geometry that flowing liquid makes and nothing else makes. Tributaries joining at acute angles, channels deepening downstream, whole systems draining in a consistent direction toward a boundary that looked, unmistakably, like a coastline. Nobody on Earth had seen a river valley on another world in that kind of detail before. Mars has valley networks, ancient and dry, cut by water that stopped flowing billions of years ago. Titan's looked recent. They looked, in the flat language of the descent report, like terrain that had been rained on. The lander came down on the dark plain, just past the mouth of the drainage, at about 10 degrees south of the equator. It survived the impact, kept transmitting from the surface for more than an hour, and returned the only ground-level photograph anyone has ever taken beyond the asteroid belt. The picture is worth describing precisely, because almost every large conclusion about Titan's liquid rests on it. The ground in the image is a flat, dark surface strewn with pebbles. The pebbles are a few centimeters across. They are made of water ice, and they are rounded. Not fractured, not angular. Rounded in the way that stones in a stream bed are rounded by being tumbled against each other in a moving fluid for a long time. They also sit in a size-sorted arrangement, with the coarser material where a current would drop it, which is what a flowing liquid does to a bed of loose sediment and what nothing else does. The way the probe stopped tells the same story. The impact deceleration recorded on landing was not the sharp shock of hitting bedrock or the long crush of hitting powder. It matched a surface with a thin, slightly cohesive crust over damp, packed granular material underneath, something closer to a riverbed after the water has gone down than to a desert or a rock plain. Then came the measurement that settled the argument. Huygens carried a gas chromatograph and mass spectrometer, an instrument that samples the air and reports what is in it, molecule by molecule. It had been sniffing Titan's atmosphere all the way down. About 2 minutes after the landing, the methane signal rose abruptly by roughly 40%. Nothing had changed in the sky. What had changed is that a warm instrument inlet was now sitting on the ground at minus 179 degrees Celsius, and the ground had begun to give up its volatiles. The probe had warmed the soil by a few degrees, and the soil had exhaled methane. That is the whole case for a damp world, and it is a strong one. Rounded ice pebbles, sorted sediment, a surface with give in it, and liquid methane held in the ground, close enough to the surface that a small amount of waste heat from a lander could pull it back into the air. To understand what happens next, you have to accept a substitution that the mind resists. On Earth, we sort materials into 3 loose categories without thinking about it. Some things are rock. They hold shape, they bear load, they erode slowly. Some things are liquid. They flow, they pool, they carry sediment. Some things are gas. They mix, they rise, they carry weather. Which category a substance falls into is not a property of the substance. It is a property of the temperature. Water on Earth sits close to all 3 of its states at once. That is unusual, and it is the reason our planet has weather at all. Water freezes at 0 degrees Celsius and boils at 100, and Earth's surface averages about 15. Which places the whole planet inside water's liquid range with margins on both sides. Ice at the poles, vapor in the air, ocean in between. One substance, 3 phases, in constant exchange. Titan sits at minus 179. Water at that temperature is nowhere near melting. It has no vapor pressure worth measuring. It is, in every functional sense, a mineral, and it behaves like one. Titan's crust is water ice, and it holds mountains, it fractures, it forms cliffs, it takes an impact crater and keeps the rim. When we say a canyon wall on Titan is 570 meters tall, we are describing a wall of water standing up like sandstone, which leaves the liquid roll open. On a world that cold, almost every familiar substance is frozen solid, and the ones that are not are frozen so thoroughly they are useless. But methane freezes at about minus 182 degrees Celsius and boils at about minus 161 at Titan's pressure. Titan's surface temperature falls inside that window. Not comfortably inside it, near the cold end of it, with only a few degrees of margin, but inside. So the roles are simply reassigned. Water takes the part that rock plays on Earth. Methane takes the part that water plays. And nitrogen, which on Earth is an inert bystander in the air, becomes the atmosphere's overwhelming bulk, exactly as it is here, for entirely different reasons. Once you accept the substitution, The rest of the system follows with an almost tedious familiarity. A liquid sitting in an open basin under an atmosphere will evaporate until the air above it reaches saturation. That is not a fact about water. It is a fact about liquids. On Titan, the seas are almost entirely at the North Pole, and above them the air carries methane vapor in the same way the air above the Pacific carries water vapor. Huygens measured methane near the surface at about 5.5% of the atmosphere by number, and roughly 1.5% in the lower stratosphere, which tells you the vapor is concentrated near the ground and thins with altitude, the same vertical profile humidity has on Earth. Near the surface, the atmosphere sits at somewhere around half of saturation. In terrestrial terms, Titan has a relative humidity of about 50%. It is a mild, muggy afternoon by the numbers, held at a temperature that would freeze nitrogen out of a scuba tank. The consequences run in both directions. Because the air is unsaturated, standing liquid evaporates, and the smaller ponds at the poles have been observed to shrink and vanish between one season and the next. Because the air holds a great deal of methane in absolute terms, and because that methane is far heavier per particle than water vapor is in our air, Titan can precipitate an enormous quantity of liquid when conditions change. And the conditions do change slowly. Titan orbits Saturn every 15 days and 22 hours, but the seasons do not belong to Titan. They belong to Saturn, whose year lasts about 29.5 Earth years. Divide that into 4, and each Titan season runs a little over 7 Earth years. Spring at the North Pole lasts longer than most careers. That is the tempo the whole hydrological system, and it is a hydrological system in every respect but the molecule, operates on. Storms are not annual. Droughts are not seasonal in any sense a farmer would recognize. On Titan, weather is measured against a clock that ticks once a decade, and the evidence for it has to be gathered by a spacecraft that only visited every few weeks. Cassini spent 13 years in the Saturn system and made well over 100 close passes of Titan. And one of the quieter achievements of that mission is that it watched a cloud population move. For the first years of the mission, the clouds were where the model said they should be, clustered near the South Pole, which was in summer when Cassini arrived, and appearing in bright convective bunches over a region already known to hold lakes. They were not large by terrestrial standards. They did not last long, and they came and went over days, but they were unambiguous. Something in that atmosphere was condensing and falling out. Then the seasons turned. Saturn passed equinox in August 2009. Sunlight shifted toward the northern hemisphere, and the cloud activity followed it. Slowly, over years, in the way a very large and very cold system responds to a very small change in heating. Mid-latitude bands appeared. The south polar clouds thinned. A vortex formed over the South Pole as it moved into winter, and the northern lakes came out of a decade of darkness into continuous light. None of this happened quickly enough to watch in the ordinary sense. A terrestrial meteorologist studies a storm over an afternoon. Titan's cloud climatology had to be assembled from snapshots taken weeks apart, across more than a decade, and even then it covered only about half a Titan year. There is one more feature worth naming because it is the gentlest weather anywhere we have looked. Near the South Pole, Cassini's spectrometer detected fog, a thin, low-lying layer of methane haze hugging the ground, the kind that forms when a damp surface cools and the air just above it reaches saturation. Fog is not a dramatic observation, but fog is diagnostic. Fog requires liquid at the surface, in contact with the air, in sufficient quantity to humidify the layer directly above it. You cannot get ground fog from a dry world. So by the middle of the mission, the picture was already coherent. There was liquid on the ground. There was vapor in the air. There were clouds forming out of that vapor at the poles and drifting through the mid-latitudes as the seasons moved. Every stage of a cycle was accounted for except the one that matters most to anyone standing underneath it. Nobody had caught it raining. Here is the thing nobody likes to say plainly. No spacecraft has ever photographed rain falling on Titan. Not one frame. Everything we know about Titan's rainfall is inferred from what the rain did after it landed. The clearest case came in late 2010. Cassini's imaging cameras had been monitoring the equatorial regions, which were expected to be arid, dune country, the driest terrain on the moon. In September of that year, an unusually large cloud system developed at low latitudes and spread over several weeks. White clouds at the equator were themselves a notable event, since the models had predicted equatorial storms near equinox, but had not yet seen one. Then in October, the ground changed. Along the southern boundary of Belet, an enormous dune field near the equator, a region of roughly 500,000 square kilometers, had gone visibly darker. Smaller patches nearby had darkened as well. The change was measurable and it was large. Some of the brighter terrain along that margin dropped in brightness by more than 10%. Darkening on its own proves nothing. Ground can darken for many reasons. What made this observation load-bearing was what happened next. Parts of the darkened region began to recover almost immediately. By the 29th of October, only some of the area was still dark. By the 15th of January the following year, more of it had reverted to its previous brightness. That sequence, a storm, then a large dark patch, then a slow return to normal, is the signature of wetting and drying. Wet ground is darker than dry ground on Titan for the same reason it is darker on Earth. A liquid film changes how the surface scatters light, and a wet patch that dries out from the edges inward over weeks is behaving exactly like a puddle field in a desert after a rare storm. So the honest statement is this: we did not see rain. We saw a cloud system arrive over the driest region of Titan. We saw 500,000 square kilometers of that region turn dark in a way that only a liquid film explains well, and we watched it dry out over the following months. On Earth, we would call that a rainfall event and move on. On Titan, it is worth stating the chain of inference out loud, because the chain is the evidence. If you could stand under that storm, with a pressure suit, a heat source, and a great deal of patience, the experience would be unlike any rain you have been caught in. Start with the drops. On Earth, a falling raindrop is limited in size by the aerodynamic forces that tear it apart. Above roughly 6.5 millimeters across, a drop breaks up before it lands. Titan's gravity is about 1/7 of Earth's, and its air is dense, and both of those changes push in the same direction. drops can grow larger before anything tears them apart. Modeling gives a maximum methane drop of about 9.5 millimeters, near the size of a small marble. Then consider the fall. A large terrestrial raindrop reaches the ground at something like 9 meters per second, fast enough to sting. A large Titan drop, held back by dense air and pulled by weak gravity, descends at roughly 1.5 meters per second. That is walking pace. It is slow enough that you could watch a single drop through its final seconds, track it, and step out of its way. The drops are also, in the strict sense, warm. They are simply warm relative to a world at minus 179 degrees Celsius, which is to say they are cold enough to freeze the air out of your lungs. There is one complication, and it is the sort of thing that separates careful modeling from a good story. Some model runs find that methane drops evaporate before they reach the surface. Falling that slowly through an atmosphere that is not fully saturated, a drop spends a long time exposed and can lose itself entirely on the way down. Whether rain reaches the ground on Titan depends on the humidity of the air below the cloud, the size of the drop, and how far it has to fall. Later work found that under a reasonable range of conditions, rain and even methane hail can make it all the way. Both results can be true. Some Titan storms probably deliver drizzle that never lands, a curtain of liquid hanging beneath a cloud and dissolving in midair. Others deliver a downpour that soaks 500,000 square kilometers of dune field. The Bellet observation is evidence that at least some of it lands. The dunes themselves are the strongest argument that Titan's equator is, most of the time, extraordinarily dry. Titan's low latitudes are covered by dune fields on a scale that has no terrestrial parallel. Bellet and Shangri-La are two of the largest. Individually, they cover areas comparable to whole continents on Earth. The dunes are long, parallel, and linear, hundreds of kilometers in length and 100 meters or so in height, and they run in orderly ranks across the equatorial belt. They are not made of sand in the mineral sense. The grains are organic, solid particles built from the same photochemical products that make the haze, sifted down out of the atmosphere over geological time and accumulated on the ground. Titan's deserts are made from its own exhaust. Dunes require two things: loose grains and wind, and an absence of standing liquid to cement them into place. Their presence across the entire equatorial belt tells you that the belt spends most of its time dry enough for grains to blow freely. The rainfall statistics that come out of Titan climate models agree. At low latitudes, significant rainfall arrives perhaps once in several decades, in intense, short-lived episodes, separated by long stretches of nothing. This is a familiar pattern on Earth, just stretched. The Atacama, parts of the Sahara, the interior of Australia, all of them go years without meaningful rain, and all of them are shaped by the rain when it comes, rather than by the drought in between. A landscape does not need frequent rain to look like it was made by water. It needs enough rain, occasionally, and enough time. Titan has been running the cycle for a very long time, and its terrain shows it. Bright, rugged, elevated regions are cut by channels. Dark, low, flat regions collect what runs off them. The equator is a desert with a floodplain grammar written all over it, and once every few decades, the grammar gets used. The single most convincing river on Titan has a name, a measured length, measured depths, and confirmed liquid in it right now. Vid Flumina is a drainage network in the north, running more than 400 kilometers before it empties into Ligeia Mare, the moon's second largest sea. In May of 2013, Cassini's radar altimeter, an instrument designed to measure the height of the surface underneath it, passed directly over the network and returned a set of echoes that took years to fully interpret. Two things came out of those echoes. The first is the depth. The branches of Vid Flumina do not run in shallow scours. They run in canyons, steep-sided, narrow gorges, in places a little less than a kilometer wide, with walls standing up to about 570 meters above the channel floor. That is a canyon nearly 600 meters deep, cut into water ice by liquid methane. The second is the state of the channel bottom. The altimeter returned strong specular reflections from the floors of those canyons, the sharp, mirror-like echo you get from a flat, smooth surface, and specifically the echo you get from a liquid surface rather than a rough, solid one. The canyons are not dry gorges left by an earlier climate. They are currently full. There is a further detail that turns the measurement into a system. The liquid surfaces inside the canyons sit at essentially the same elevation as the surface of Ligeia Mare itself. The rivers are not perched above the sea. They are graded to it, the way a tidal estuary on Earth is graded to the ocean it opens into. Vid Flumina is the drowned lower reach of a river system whose sea level has risen to meet it. To cut a canyon that deep, you need sustained flow over a long period, or repeated catastrophic flow, or a surface that has been uplifted while the river kept pace, and probably some combination. Whichever mechanism dominates, the implication is the same. This is not a fossil landscape. Titan has running rivers at this moment feeding a sea. The shapes of Titan's channel networks carry information beyond the fact that they exist, and reading them is one of the more elegant pieces of work to come out of the Cassini radar data. Some Titan drainages are dendritic. They branch like a tree, or like the veins on a leaf, with tributaries entering at consistent acute angles and the whole network converging toward a single outlet. On Earth, dendritic networks form where the ground is relatively uniform, and the flow simply finds the steepest path down. They are the signature of rainfall over an undifferentiated surface, water landing everywhere and organizing itself on the way down. Other Titan drainages are rectilinear. They run in long, straight segments and turn at sharp, near right angles. On Earth, that pattern means the liquid is not choosing its own path. It is exploiting a pre-existing weakness, a fault, a joint set, a fracture system in the bedrock. Vid Flumina's deep canyons follow this kind of structural control, which is part of why they are narrow and deep rather than broad and shallow. So the channel map is telling two stories at once. Where the networks branch like trees, methane rain is falling on the landscape and running off it. Where they run in straight lines and turn at corners, the ice crust underneath is fractured, and the liquid is following the cracks. That second point matters more than it first appears. A fractured crust is a crust that has been deformed by tidal flexing from Saturn, by cooling and contraction, by whatever is happening in the interior. It also means the surface is permeable. Liquid entering those fractures does not necessarily stay on the surface. It can move through the crust, out of sight, between basins. That idea has a name in the Titan literature, an alkanopher. It is the direct analog of an aquifer, with liquid hydrocarbons in place of groundwater, held in the pore space and fracture network of an ice bedrock. And as we are about to see, the seas themselves behave as though something like that is real. Return for a moment to the pebbles in the Huygens photograph, because the sediment is the part of Titan's cycle that closes the argument. A river does three things to solid material. It breaks it carries it, and it sorts it. Angular fragments knock against each other in transport and lose their corners. The longer the transport, the rounder the result. Larger class drop out first when the current slows. Finer material travels further, and the deposit ends up graded by size along the flow path. Every one of those effects is mechanical. None of them depends on what the liquid is made of, only that it flows with enough energy to move grains. The Huygens landing site shows all three. The ice pebbles are rounded, which means they were tumbled. They are sorted, which means they were carried by a current that lost energy. And they sit on a flat, low plain immediately downstream of a visible drainage network, which is exactly where a river deposits its load when it reaches a basin. At the other end of the size scale, the dune grains tell the complementary story. They are fine, they are organic, and they are mobile, moved by wind rather than by liquid, but assembled out of material that fell out of the sky. Between the two, Titan has a complete sedimentary system: production of particles in the atmosphere, delivery to the surface, transport by wind across the equator, transport by liquid down from the highlands, and deposition into basins and seas. Sediment is also why the seas are not clean. Radar analysis of the seafloor beneath Ligeia Mare points to a layer of organic rich sludge on the bottom. Material that arrived as haze particles was carried in by rivers or fell directly onto the surface and accumulated where the current stopped. The floor of a Titan sea is not bare ice. It is a soft accumulation of the same chemistry that clouds the sky. Which brings us to the seas themselves. They are the reason this episode exists. They are the only large standing bodies of liquid known outside Earth, and they have been measured with a precision that ought to be impossible from a spacecraft passing at speed, hundreds of kilometers up, through a moon's worth of haze. Before going any further into the seas, it is worth being clear about how any of this was measured, because the method shaped what we know and what we do not. Cassini launched on the 15th of October 1997 and arrived at Saturn on the 1st of July 2004 after a cruise of nearly 7 years. It carried Huygens to Titan 6 months later and then spent the next 13 years in orbit around Saturn, ending on the 15th of September 2017, when it was deliberately flown into the planet to avoid ever contaminating a moon. Over that period, it made 127 targeted close flybys of Titan, the last of them on the 22nd of April 2017. 127 is a large number of encounters, and it is also, in a specific sense, a small one. Each flyby lasted hours, not days. The spacecraft came in fast, gathered what it could along a narrow track beneath its path, and left. The radar could not image the whole moon at once. It imaged strips, long narrow ribbons of surface at varying resolution, laid down one encounter at a time. Titan's global radar map is not a photograph. It is a mosaic assembled from more than a decade of ribbons, with gaps between them at resolutions that change from one strip to the next. The altimeter is narrower still. When you read that Ligeia Mare is 160 meters deep, that number comes from a single line drawn across the sea during one pass in May 2013. Not a survey, a line. Everything about the shape of that seafloor away from the track is interpolation and inference. This is the ordinary condition of planetary science, and it deserves stating plainly rather than being smoothed over. We have one ground truth site on Titan, occupied for a little over an hour by a probe that was never designed to move. We have one properly sounded sea. We have a global map assembled from strips gathered over 13 years by a spacecraft that never orbited the moon itself, only past it. What is remarkable is how much structure came out of that. Coastlines, drainage networks, dune orientation, canyon depths, sea composition, cloud seasonality, a global sea level. Sparse data, patiently accumulated and carefully modeled, produced a coherent picture of an entire hydrological system on a body more than 1 billion kilometers away. It also means the picture has a resolution limit, and that limit is why so many of tonight's statements come with a qualifier attached. When the answer is "we measured it," the sentence says so. When the answer is "the models require it," the sentence says that instead. On Titan, the gap between those two categories is unusually wide, and it is about to get wider. Start with how much liquid there is and where it is. Radar mapping over the course of the Cassini mission covered most of Titan's surface at varying resolution, and the lakes and seas show up in that data with almost unfair clarity. Radar works by sending a pulse down and listening for what comes back. A rough surface scatters the pulse in all directions and returns a portion of it. A perfectly smooth surface reflects it away like a mirror, and unless the geometry is exactly right, nothing comes back at all. On a radar map, a body of standing liquid is not a feature you have to look for. It is a hole in the image, an area of near total darkness with a sharp, closed boundary. Counting those dark shapes gives a total. More than 1.6 million square kilometers of Titan is covered in liquid, which works out to nearly 2% of the moon's surface. 2% sounds modest until you place it. Earth's surface is about 71% ocean, so by fraction, Titan is far drier than we are. But 2% of a body 2,500 kilometers in radius is a great deal of standing liquid, comparable in area to all of Earth's Great Lakes several times over, and made of a substance that on Earth we ship in pressurized tanks. The distribution is the strange part. Almost all of it is in the north. The northern high latitudes hold 3 large seas and hundreds of smaller lakes, some of them steep-sided and sharply defined, arranged over a broad polar region. The southern polar region holds a fraction of that, one significant lake and a scattering of smaller features, most of them shallow, Several of them observed to shrink. Why the liquid is concentrated in one hemisphere is a live question. The leading explanation involves Saturn's orbit. Saturn's path around the Sun is slightly eccentric, so Titan's southern summer is shorter and more intense, while its northern summer is longer and milder. Over long periods, that asymmetry can drive a net transport of methane from one pole to the other, and the current arrangement may be one phase of a cycle that reverses over tens of thousands of years. If that is right, then the seas we are looking at are not permanent geography. There are hemispheres worth of liquid parked at one end of the moon, on its way, very slowly, to the other. Kraken Mare is the largest of them, a sprawling, many-lobed sea in the north with a complicated coastline, several distinct basins, narrow straits between them, and inlets that look for all the world like drowned river valleys. Laid over Earth, its area would swallow the Caspian Sea and keep going. Measuring the depth of something like that from orbit should not be possible. It turned out to be possible because of an accident of chemistry. Liquid methane is remarkably transparent to radio waves at the wavelength Cassini's radar used. That means the radar could function as a sounder. The pulse enters the liquid, travels down, reflects off the seafloor, and comes back, and the delay between the surface echo and the bottom echo gives you the depth directly. It is the same principle as a fishing boat's depth finder, operated from a spacecraft moving at several kilometers per second, hundreds of kilometers overhead, through an opaque atmosphere. Over the shallower margins of Kraken Mare, near a flooded river valley on its edge, the technique worked and returned depths in the range of 20 to 35 meters. Over the central basins, it failed. The pulse went in, and nothing came back from below. A failed measurement is still a measurement. The absence of a seafloor echo constrains the answer in two directions at once. Either the sea is deeper than the sounder can reach, which is roughly 200 meters, or the liquid is more absorbing than pure methane, richer in ethane, which soaks up the signal, or both. Later analysis of the same data set inferred central depths that may reach about 300 meters. Either way, the honest summary is the interesting one. On the largest sea on Titan, we sent a pulse of radio energy down through the liquid and never heard it hit the bottom. Ligeia Mare is smaller, the second of the three great northern seas, and it is the one place on Titan where the full measurement worked. In the same May 2013 pass that found the canyons of Vid Flumina, Cassini's altimeter crossed Ligeia Mare and returned a clean pair of echoes, one from the liquid surface, one from the seafloor beneath it. The delay between them gave a depth profile along the track, and the deepest point on that profile came out at about 160 meters. That is a real sea. 160 meters is deeper than most of the North Sea you could name. A ship could operate on it. A submarine could dive in it, and several mission concepts have proposed exactly that. The same measurement carried a bonus. How much a radio pulse is attenuated on the way down and back depends on what it passed through, so the strength of the seafloor echo constrains the composition of the liquid above it. A methane-rich liquid is nearly transparent and returns a strong bottom echo. An ethane-rich liquid absorbs more and returns a weak one, or none. Ligeia's bottom echo was strong. Combined with an independent analysis of the sea's microwave thermal emission, its natural glow at a wavelength of 2.2 centimeters, monitored from 2007 through 2015. The conclusion was that Ligeia Mare is dominated by liquid methane rather than ethane. There is a second finding from that thermal work, and it deserves its own sentence. The seafloor of Ligeia is likely covered by a layer of organic-rich sludge, the settled remains of atmospheric haze and river-borne sediment. So we have one sea, properly sounded, 160 meters deep at its center, made mostly of methane, with an organic ooze on the bottom. That is more than we knew about most of Earth's ocean floor a century ago. The three great seas take most of the attention, but the northern terrain around them holds hundreds of smaller lakes, and those are stranger than the seas in a way that took years to appreciate. Some are exactly what you would expect: irregular, branching shapes with drowned valleys running into them, clearly the flooded lower ends of river systems. Others are nothing like that. They are small, close to circular, and startlingly steep-sided, sitting in depressions with raised rims around them, a ring of elevated terrain standing above the surrounding plain, as though the ground had been pushed up from below before the hole formed. That morphology does not fit a river-cut basin, and it does not fit the first explanation people reached for either. Dissolution was the natural candidate. On Earth, limestone dissolves in slightly acidic groundwater and leaves closed depressions, sinkholes, and lake basins, the whole family of landforms called karst. Titan has soluble solids at its surface, the organic material raining out of the atmosphere, and it has a liquid that can dissolve them. A karst analog seems straightforward. The trouble is the rims. Karst depressions on Earth do not have raised rims. Ground collapses into a dissolution cavity, and the surface goes down, not up. The alternative that has gained ground is more violent. If liquid nitrogen, dissolved in the crust during a colder period, becomes unstable as conditions warm, it can flash to vapor near the surface and blow out a crater, the same mechanism that produces Mare craters on Earth when rising magma meets groundwater and the water explodes. That process makes a hole with an elevated rim of ejected material around it, which is what the images show. Modeling published in 2019 found this explanation viable for the small rimmed northern basins, and later work has continued to assess how such an explosion could work in Titan's crust. If that is right, then some of Titan's lakes are not erosional features at all. They are explosion craters that later filled with rain. There is one more feature of the lake country worth carrying with you. Around the shores of many lakes and across the floors of ones that have gone dry, the infrared instruments found deposits that are unusually bright at a wavelength of 5 micrometers. The interpretation is evaporite, material that was dissolved in the liquid and left behind as a crust when the liquid evaporated away. On Earth, drought exposes exactly this: the pale bathtub rings around a shrinking reservoir made of the minerals the water was carrying. Titan has bathtub rings. They are made of organics rather than carbonate. They mark liquid levels that have fallen within the past few decades, and they are one of the more human-scale things anyone has found in the outer solar system. A shoreline that has moved is a shoreline with a history, and the pale band above the current edge is that history written down in a substance that was carried there dissolved and left behind when its solvent went back into the sky. This is where precision matters more than anywhere else in tonight's story, and where it is easiest to say something false while sounding confident. It is common to hear that Titan's seas are made of methane. It is equally common to hear that they are made of ethane. Both statements are too flat to be true. The liquid on Titan is a mixture, principally methane and ethane, with dissolved nitrogen and traces of propane and heavier compounds, and the proportions are not the same from one basin to the next. Ligeia Mare, as we have just seen, comes out methane-dominated in the radar and radiometry analyses. Ontario Lacus, the largest lake in the southern hemisphere, gave a different answer. In December 2007, Cassini's visual and infrared mapping spectrometer observed Ontario Lacus during a close pass and found a spectral absorption near 2 micrometers that was interpreted as liquid ethane, probably in solution with methane, nitrogen, and other hydrocarbons. And here's the part that gets left out of the summaries. That interpretation has been contested. A later analysis argued the same absorption feature may sit in the terrain surrounding the lake rather than in the lake itself, and that it could indicate damp sediments, ethane, propane, methane, and minor components soaked into the shoreline material as the lake retreated by evaporation. So the careful version of the sentence is this: Titan's liquid is a hydrocarbon mixture. One northern sea has been measured as methane-dominated with 2 independent radar techniques. One southern lake shows a spectral signature interpreted as ethane, with an active dispute about whether that signature comes from the lake or from its wet margins. Everywhere else, we are extrapolating. If that sounds like a retreat from the confident version, it is worth remembering what is actually on offer. We are arguing about the relative concentration of 2 specific molecules in a specific basin on a moon of Saturn, from measurements taken by an instrument that flew past at speed. The disagreement is a sign of how close the measurements are getting, not how far away they are. The composition question turns out to be a doorway into the real problem, and it opens through a simple piece of accounting. Sunlight has been breaking methane apart in Titan's upper atmosphere for a long time. The primary product of that chemistry is ethane. Every methane molecule destroyed high up is, in effect, a small deposit into an ethane account, and the deposits have been running continuously. Run that production rate over the age of the solar system, and the numbers get uncomfortable. The photochemistry, sustained for billions of years, should have delivered an enormous quantity of ethane to the surface, enough, by many estimates, to fill the basins far beyond what we observe, potentially to a global depth of hundreds of meters. We do not see that. The observed liquid inventory is far smaller, and the one sea we have measured properly is methane-dominated rather than ethane-choked. Somewhere between the production and the observation, the ethane has gone missing. There are ways to make the books balance, and the leading one is that the ethane is not gone, it is stored. Beneath the seas, in the porous ice crust, water molecules can form cage-like structures called clathrates, and those cages preferentially trap ethane over methane. Modeling of that process shows something specific and useful. Progressive entrapment of ethane in an underlying clathrate layer will drive the remaining surface liquid toward a methane-dominated composition for essentially any plausible starting mixture. That single mechanism explains two observations at once. It explains why Ligeia reads as methane-rich despite billions of years of ethane production, and it explains where the missing ethane has gone. Into the floor, sequestered in ice cages, out of sight of every instrument we have. It is a satisfying answer. It is also, at present, a model. Nobody has drilled into the bed of a Titan sea. The clathrate layer is inferred from chemistry and thermodynamics, not sampled, and the distinction between those two categories is the through line of everything left in this episode. There is one more thing Cassini learned about the seas, and it is the detail that makes them hardest to picture. They are almost perfectly flat. The evidence comes from the radar again, used in a different mode. In a bastatic experiment, the spacecraft transmits toward the surface and the signal bounces off at an angle to be received back on Earth. The shape and polarization of the returned signal encode how rough the reflecting surface was, down to scales of centimeters. Applied to Titan seas, the technique returned some of the smoothest surfaces ever measured anywhere. Wave heights, where they could be constrained at all, came out at a few millimeters. Not meters, millimeters. For most of the mission, the great northern seas of Titan were as still as a sheet of glass, disturbed only occasionally, and even then barely. Part of the reason is the winds, which are extremely light near the surface. The thick, cold air moves slowly, and the dense atmosphere damps what motion there is. Part of it is the liquid, which is far less viscous than water and responds differently to the wind that does arrive. And part of it is the season. During the years Cassini watched most closely, the northern seas were coming out of winter, and the winds that theory says should eventually stir them had not fully arrived. Against that stillness, one anomaly became famous. In a region of Ligeia Mare, a bright feature appeared in the radar data where nothing had been before, then vanished, then reappeared in a later pass with a different shape and extent. It was nicknamed the Magic Island, and it was joined by similar transient features elsewhere. Nobody has settled what they are. Candidates include waves in a patch of locally roughened surface, bubbles of nitrogen released as the liquid warms and its dissolved gas comes out of solution, floating solids or suspended material rising from the bottom. Each of those is a real physical process. Each would produce a bright transient patch, and no observation to date discriminates between them cleanly. It is one of the few genuinely unresolved features of a place at minus 179 degrees Celsius that otherwise refuses to do anything sudden. The last discovery from the sea data is the quietest and the most consequential. Altimetry across the northern seas established their surface elevations to reasonable precision, and the numbers came back nearly identical. Kraken Mare, Ligeia Mare, and Punga Mare all sit at effectively the same level, within the uncertainty of the measurement. The smaller lakes scattered across the northern terrain, however, sit at a range of higher elevations, each one perched in its own local basin. On Earth, a shared surface level across separate bodies means one thing. The Atlantic and the Pacific stand at the same height because they are connected physically through channels, and the liquid finds its own level across the entire connected system. That is what sea level means, a single equipotential surface maintained by flow. Titan's three great seas are partially connected on the surface through visible straits, but the more interesting inference is what the shared level implies about the ground between them. If the ice crust is porous and fractured, and the rectilinear channel networks say it is, then liquid can move through the subsurface from one basin to another, and the seas are the exposed upper surface of a much larger connected reservoir held inside the crust. That is the Alkanoffer idea again, and the sea level measurement is its strongest support. The visible seas would then be less like isolated lakes and more like the places where a regional water table happens to intersect the ground, the way an oasis is not a separate body of water, but a window onto one. It also changes the accounting problem in a direction that matters. If there is liquid inside the crust as well as on it, then the total reservoir is larger than the radar dark shape suggests. And the question of how much methane Titan actually has and how long it can last gets harder to answer from orbit, which is exactly the question we have been walking toward. Everything described so far, the clouds, the rain, the rivers, the canyons, the seas, the sorted pebbles on the plain where Huygens came to rest, depends on one condition. There has to be methane in the atmosphere. Take the methane out and the entire system stops in a specific order. No methane vapor, no clouds. No clouds, no rain. No rain, no runoff. No rivers, no resupply for the seas. And critically, no methane means no haze, because the haze is nothing but methane that has been taken apart and reassembled into heavier molecules. The trouble is that the atmosphere is dismantling its own methane continuously, and has been for as long as the sun has been shining on it. The chemistry is not subtle. Ultraviolet photons and charged particles break the carbon-hydrogen bonds in methane in the upper atmosphere. The fragments do not go back together as methane. They combine into ethane, acetylene, propane, and progressively longer chains, and those products are heavier, less volatile, and end up on the ground. Hydrogen, the other product, is light enough to escape Titan's gravity entirely and is lost to space. That is a one-way reaction. Methane goes up as methane and comes down as something else. It does not cycle back. Put a rate on it, and the time scale is short in geological terms. Photochemical models find that Titan's entire atmospheric methane inventory should be destroyed in something on the order of tens of millions of years, commonly quoted around 30 million years, with a plausible range of 10 to 100 million depending on assumptions. 30 million years sounds like a long time until you compare it to the age of the object it is sitting on. Titan is roughly 4.5 billion years old. 30 million years is less than 1% of that. If you compress Titan's history into a single calendar year, the atmosphere's entire methane supply would be consumed in under 3 days. So here's the question the rest of this episode exists to sit with. If the methane runs out in 30 million years, and Titan has been here for 4.5 billion, why is there any methane left at all? The obvious answer is the one we have spent most of tonight looking at: the seas. If the atmosphere is losing methane, the seas can top it up. Liquid evaporates, vapor enters the air, The reservoir on the ground draws down slowly and the atmosphere stays supplied. That is how it works on Earth. The ocean is enormous compared to the atmosphere, so the water in the air is a rounding error against the water in the sea. On Titan, the accounting does not work. The surface reservoir simply is not large enough. Total the known lakes and seas, more than 1.6 million square kilometers of liquid, with depths ranging from tens of meters to perhaps 300 at the deepest known point. And you get an impressive quantity of hydrocarbon by any human standard. Compared with Earth's proven reserves of oil and natural gas, Titan's known surface inventory is larger by a wide margin, which is a fact people enjoy quoting. Compared with what the atmosphere destroys over geological time, it is nothing like enough. Published analyses are consistent on this point. The observed surface reservoirs cannot have sustained the present atmospheric methane abundance across billions of years. Even generous assumptions about liquid hidden in the crust, the alkanophore, the pore space, the fractures, struggle to close a gap that large. That leaves two possibilities, and both of them are uncomfortable. The first is that something is actively resupplying the atmosphere from inside Titan on a schedule and has been doing so repeatedly. The second is that the atmosphere we are looking at is not 4.5 billion years old at all. That Titan's thick methane air is a relatively recent development that we happen to be watching during an unusual interval, and that for most of its history, this moon looked nothing like it does tonight. Neither option is comfortable, and the evidence does not currently exclude either one. This is not a case where the textbook answer exists and the public summary is simply behind. There is no textbook answer. What there is, instead, is a short list of candidate mechanisms, each supported by real physics, none of them observed in action. The first and most developed is episodic outgassing from a clathrate reservoir. Deep in Titan's interior, methane can be locked inside cages of water ice, held under pressure above an internal ocean rich in ammonia. Thermal and structural evolution of the interior can, at intervals, destabilize part of that reservoir and release a pulse of methane upward through the crust and into the atmosphere. Modeling of Titan's interior evolution has identified specific episodes when this would occur, associated with major changes in how heat moves through the moon, with long, quiet stretches in between. The second is chemical production at depth. Where liquid water contacts certain silicate minerals, a reaction called serpentinization produces hydrogen, and that hydrogen can react with available carbon to make methane. This is not exotic chemistry. It happens on Earth's seafloor at hydrothermal vents. If Titan's internal ocean is in contact with a rocky core, the same reaction can run there, manufacturing new methane from raw materials rather than releasing stored methane. The third is impacts. If a layer of methane clathrate sits within Titan's crust, then a large impact that punches through it will release the trapped methane directly. Recent modeling of crater-forming impacts into a clathrate crust finds that this can deliver meaningful quantities of methane to the atmosphere, episodically, over the moon's history. Notice what all three have in common. Each one is a plausible mechanism, worked out in detail, published, and defensible, and not one of them has been caught happening. Nobody has observed an outgassing event. nobody has measured the internal ocean directly. There is no confirmed cryovolcano on Titan. Several candidate features have been proposed from radar imagery, and each has an alternative explanation that does not require anything erupting. The methane arrived from somewhere. Every proposed somewhere is a model. It is worth taking the failure case seriously because it is not a hypothetical curiosity. It is the default outcome if nothing resupplies the atmosphere. Remove the methane, and the first thing that goes is the haze, since the haze is made from it. Over some period, the orange smog thins and clears, and for the first time in a very long while, sunlight reaches Titan's surface undiminished and the sky becomes transparent. That change is not benign. The haze is a significant part of what keeps the surface as warm as it is. It absorbs sunlight aloft, and the methane itself contributes to a greenhouse effect in the lower atmosphere. Take both away, and the surface cools further from a starting point of minus 179 degrees Celsius. Cool nitrogen enough, and it stops behaving like air. The published version of this scenario is a photochemically driven collapse. With the methane gone and the temperature falling, a substantial fraction of Titan's nitrogen atmosphere condenses out and falls to the ground as liquid or frost. The pressure drops. The seas, already unfed, evaporate or freeze. What is left is a cold, bright, still ice world with a thin remnant atmosphere and no weather at all. There's a real possibility, taken seriously in the literature, that Titan has done this before, that its climate is episodic rather than continuous, that there have been long stretches, most of its history, possibly, with a thin atmosphere and a dead surface, punctuated by intervals of a few tens of millions of years when a pulse of methane arrives from below. The haze builds, the greenhouse warms the ground, the clouds form, and the rain starts again. If that is what is happening, then everything in tonight's episode is a description of a phase, not a place. The rivers are real, but they are the rivers of an interval. The seas are real, but they are the seas of a warm chapter in a book that is mostly cold. And the fact that we arrived with a spacecraft during one of the rare wet intervals is not a coincidence that requires explanation. It is simply what happened, and we do not get to know the odds. There is one more inversion in this story, and it is the one that closes the title. Titan has an enormous quantity of water. It is one of the wettest bodies in the solar system by mass fraction. It has, by most estimates, considerably more water than Earth does. None of it can rain. The upper part of it is the crust, a shell of water ice, tens of kilometers thick, that serves as the moon's bedrock. That is the material the canyons of Vid Flumina are cut into, the material the rounded pebbles at the Huygens site are made of, the material the seafloor of Ligeia consists of underneath its organic sludge. Every landform on Titan is a landform in water. The lower part is an ocean. Analysis of Huygens data, together with gravity measurements from Cassini's flybys, supports a global layer of liquid water beginning roughly 55 to 80 kilometers beneath the surface, kept liquid by internal heat and by dissolved ammonia acting as antifreeze, and held in place under a lid of ice. So Titan has a hydrosphere in the literal sense. It simply has it in the wrong place and at the wrong temperature to do anything visible. The water is either load-bearing rock or a buried sea under 50 kilometers of it, and neither of those participates in weather. Meanwhile, the substance that does the weathering fills the basins, cuts the canyons, and falls out of the clouds is a fuel, a molecule that on Earth we extract from underground, compress into pipelines, and burn for heat. On Titan, it is groundwater. The plumbing is inverted from top to bottom. The pipes are made of ice, the water is the rock, and the gas main is the sky. That inversion is the honest content of the title. Titan has rain, rivers, and seas. It also has more water than we do. The two facts have nothing to do with each other. There is a reason people care about this particular moon beyond the pleasure of a strange landscape, and it comes from the same chemistry that causes all the trouble. Titan's atmosphere is an organic factory running without supervision. Sunlight breaks methane and nitrogen apart at high altitude. The fragments recombine, and the products get progressively more complex the further down they drift. The inventory detected in Titan's air includes ethane, propane, acetylene, hydrogen cyanide, benzene, and a long tail of nitrogen-bearing organics. The solid material that eventually falls out, the stuff the dunes are made of, is a mixture of large, complicated carbon-nitrogen compounds produced by no living process whatsoever. Deliver those compounds to liquid water, and interesting things happen. Hydrogen cyanide in water produces amino acids, among other products, through chemistry that has been run in laboratories since the 1950s. On Titan, the organics are abundant and the liquid water is 50 kilometers down, and under normal conditions, the two never meet. Impacts change that. A large impact into an ice crust deposits an enormous quantity of energy and melts a substantial volume of the target. For a period afterward, thousands of years by most estimates before it refreezes, there is a pool of liquid water sitting in the crater floor in direct contact with a surface layer of organic material that has been accumulating from the sky for millions of years. That is a natural laboratory, and it has run repeatedly across Titan's history, in every impact crater on the moon, without anyone setting it up. It is important to say what this is and is not. It is not a claim that anything lives on Titan. There is no evidence for biology there, and the surface conditions are severe by any standard. What it is, precisely, is the observation that Titan performs an experiment we cannot perform: complex organic chemistry delivered to liquid water at scale over geological time on a body we can reach and land on. Which is why the next spacecraft going there is not a lander at all. NASA's Dragonfly is a nuclear-powered rotorcraft, an octocopter with 4 pairs of rotors, designed to fly through Titan's atmosphere, land, sample the ground, and take off again, repeatedly, over a mission lasting years. It is a design that only makes sense in one place. Titan's atmosphere is dense, and its gravity is weak, which together make flight far easier there than on Earth. A person with strapped-on wings could plausibly get airborne under their own power. A rotorcraft on Titan can carry a full science payload for tens of kilometers on a single flight, land somewhere new, and do it again after recharging. The mission is scheduled to launch in July of 2028 aboard a Falcon Heavy and to arrive at Titan in 2034. Its destination is the equatorial region, the Shangri-La Dune Field, and the Selk Impact Crater at its edge. A relatively young crater about 90 kilometers across, chosen precisely because it is a place where impact melt once brought liquid water into contact with surface organics. Dragonfly will carry a mass spectrometer to identify the chemistry of the surface material it samples, a gamma ray and neutron spectrometer to measure the composition of the ground beneath it without digging, cameras, and a full meteorological and seismic package. Over the mission, it is planned to visit a series of sites across dune terrain and crater floor. It is worth being exact about what this mission is and is not going to settle, because the temptation to overpromise is considerable. Dragonfly is not going to the seas. Its target is the arid equator, thousands of kilometers from the northern lakes, and it will not sample liquid methane in bulk. It will not drill 50 kilometers to the internal ocean. It will not directly observe an outgassing event. And if the resupply of atmospheric methane is episodic on a timescale of tens of millions of years, no mission of any design is likely to catch one in the act. What it will do is measure the composition of Titan's surface organics directly at multiple sites, including the floor of a crater where water and organics once mixed. It will measure how the atmosphere behaves at the ground over long periods, which sharpens every climate model that currently has to guess. And it will constrain how much methane is present in the near-surface material of the driest region on the moon, which is a real input to the reservoir accounting. Dragonfly has not found anything yet. It has not launched. Everything in this episode was learned before it left the ground. Step back from the specifics, and Titan makes an argument that is easy to miss while looking at the details. Every process described tonight is a process we already knew. Evaporation from a standing body, vapor transport by an atmosphere, condensation into cloud, precipitation, runoff, channel incision, sediment transport rounding and sorting, deposition into a basin, groundwater moving through porous rock, a common level across connected reservoirs. Not one of those required a new physics to explain, and not one of them is unique to Earth. What we had assumed, without ever quite stating it, is that this list belongs to water. It does not. It belongs to any substance that finds itself near its own boiling point, on a solid surface under an atmosphere, with a source of energy to drive the exchange. Water fills that role on Earth because Earth's temperature happens to sit in water's liquid range. Methane fills it on Titan for exactly the same reason, at a temperature 200 degrees lower. That generalization has consequences beyond the Saturn system. It means the ingredient list for a world with weather is not water, but a volatile near its transition temperature, and the number of substances that can qualify is larger than one. It means the search for another world with rivers is not restricted to a narrow band of distance from a star. Titan is also the practical demonstration that these systems can be genuinely alien and genuinely legible at once. A geologist trained entirely on Earth can look at a Cassini radar image of Vid Flumina and read it correctly. That is a river. Those are tributaries. That is a delta. That is a drowned valley, without knowing anything about hydrocarbon chemistry. The grammar transferred completely. Only the vocabulary changed, and that is the strange comfort in this particular moon. It is the most foreign environment anyone has landed on, and its landscape is more familiar than any other place we have been. We have talked about a moon that hid its surface for 350 years behind a haze made of its own destroyed atmosphere. We have talked about a probe that fell for 2 hours and 27 minutes and landed among rounded ice pebbles on ground that gave up methane when a warm instrument touched it. We have talked about rain we have never photographed and about 500,000 square kilometers of dune field that went dark after a storm and dried out over the following months. We have talked about drops 9.5 millimeters across, falling at walking pace, some of which may never reach the ground. We have talked about a river 400 kilometers long, running in canyons 570 meters deep, still full of liquid today. We have talked about 1.6 million square kilometers of standing liquid, almost all of it in one hemisphere, about a sea whose bottom the radar never found, and about another, sounded to 160 meters, that came back methane-dominated with an organic sludge on its floor. We have talked about ethane that should be there and is not, and about ice cages that may be holding it. And we have talked about a clock, an atmosphere that destroys its own methane in something like 30 million years, on a moon that is 4.5 billion years old, with no observed source anywhere to refill it. So what is the rain on Titan actually made of? The honest answer, stated as precisely as the measurements allow, is that it is mostly methane, mixed with ethane and dissolved nitrogen, and traces of heavier hydrocarbons, in proportions that change from one basin to another and that have been properly measured in exactly one sea. It falls as drops up to 9.5 millimeters across. It lands, sometimes. It runs downhill into canyons cut through bedrock made of water ice. It gathers into seas deep enough that our instruments could not always find the bottom. And none of it, not one drop in any basin at any latitude, is water. There is something in that arrangement worth carrying out of tonight. We tend to treat the specific chemistry of our own world as the definition of how a world works. Rain means water. Rivers mean water. A shoreline means water. Titan takes that assumption apart without any drama at all. It keeps every process and swaps the molecule, and the result is a landscape any river geologist would recognize on sight. The rules were never about the substance. They were about temperature and pressure and the fact that something in the system was sitting close enough to its own boiling point to move. Which means the familiar things in your own life are also arrangements rather than laws. The rain against the window tonight is not weather because it is water. It is weather because it is a liquid that happens to live near the edge of its own vapor on a planet that happens to hold the right temperature in an era that happens to be warm. Somewhere else, the same processes are running with a different molecule, and to whatever might live under that sky, methane rain would be the ordinary kind. It is also worth noticing how little of tonight's story required anything to be discovered from scratch. A probe fell through an orange sky and found gravel that had been tumbled in a current. A radar pulse went down through a sea and came back off the floor. A dune field went dark after a storm and dried out over the following months. Those are the observations of a field geologist made across 1 billion kilometers on a body where the rock is ice and the river is fuel. You already know how to read most of them. That is the part worth taking with you. The surface of that world sits at about minus 179 degrees Celsius. At that temperature, water is not a liquid. It is not even a substance that moves. It is stone. A shoreline of ice, a sea of fuel, rivers that are still running, a clock that should have stopped and has not. Good night.